We live in a world that is just overflowing with information. So, how do we possibly find the hidden patterns in all that noise? And maybe more importantly, how do we turn what looks like pure chaos into something we can actually use? Well, that's exactly what we're going to dive into.
I mean, really think about this. This is the central question that keeps data scientists up at night. We've got these endless streams of data coming in every single second. But what does any of it actually mean? Where do you even begin to make sense of it all?
And here's the biggest challenge. Most of this data, it doesn't come with neat little tags or categories. It's just there. It's raw. It's messy. So this is where a concept called unsupervised learning comes in. We have to teach the machine to find the structure all on its own, without any labels to guide it. It's like finding a path in a forest that has no signs.
And the number one tool we use to bring some order to all that chaos is a technique called clustering. This is our secret weapon for finding the natural, hidden groupings that are already sitting there inside the data, just waiting to be found. So here's the core idea in a nutshell. Clustering algorithms sift through all that raw data and just automatically group similar things together. A great way to think about it is like sorting a giant bag of mixed Legos. The AI sorts them into piles of similar color and shape, but, and this is the cool part, it does it without you ever telling it what the final piles are supposed to look like.
Now, to do this kind of sorting, data scientists have a whole toolbox full of specialized algorithms. Today, we're going to pull out 3 of the most important ones. And trust me, each one has its own unique personality and a very specific job to do.
First up, we've got k-means. I like to call this one the sorter. This is your reliable, straightforward workhorse. You use it when you have a pretty good idea of how many groups you're looking for, and you just need to sort everything into the right pile. It's incredibly fast, super efficient, and it's an absolute go-to for a ton of common tasks.
The way it works is actually pretty cool. It's this iterative process. You start by just telling the algorithm, hey, I want this many clusters. That's your K. Then it just randomly drops that many centers into your data. From there, it's this little 2-step dance. It assigns every data point to its closest center, and then it moves the center to the new average location of all its points. It just repeats this dance. Assign, move, over and over, until the groups settle down and stop changing. The only catch? It kind of assumes your groups are nice round blobs. If they have weird shapes or overlap a lot, the sorter can get a little confused.
But, okay, what if you have no idea how many groups you're even looking for? Well, that's where our next tool comes in handy. Meet hierarchical clustering, or as I call it, the genealogist. This tool isn't just sorting things into piles, no. It's obsessed with relationships. It wants to build you a complete family tree of your data. So unlike the sorter, you don't have to give the genealogist a number to start with. It begins by treating every single data point as its own tiny little cluster. Then, step by step, it merges the closest pairs together, building up larger and larger groups until everything is connected. The result is this beautiful tree structure. It's called a dendrogram that literally shows you how everything is related. From there, you get to decide where to cut the tree to get the number of clusters that makes the most sense. It's absolutely perfect for when you're just exploring and trying to understand the data's natural hierarchy.
All right, so our first 2 tools, they can kind of struggle with a couple of things. Clusters that aren't nice and round, and noisy data points that don't really belong anywhere. For that, we need a specialist. So let's bring in our final tool, DBSCAN, the detective. This expert isn't interested in simple sorting or family trees. Nope. The detective is all about finding dense pockets of activity and, this is crucial, identifying the suspicious outliers that just don't fit in. You see, the detective thinks in terms of density. It scans the data, looking for areas where points are packed really closely together. Those become the clusters, and they can be any shape at all. A long, winding line, a crescent moon, you name it. And here's its real specialty. Anything that isn't part of a dense neighborhood gets flagged as noise, an outlier. It's the perfect tool for finding that one odd thing out, which is something the other 2 algorithms just aren't built to do. So let's just quickly put them all side by side. You've got k-means, the sorter, which is your best bet when you need to efficiently sort things into a set number of big, roundish groups. Then you've got hierarchical, the genealogist, for when you want to explore all the relationships in your data without deciding on the number of groups beforehand. And finally, you have DBSCAN, the detective, your specialist for finding those weirdly shaped clusters and spotting anomalies in a sea of noise.
Okay, that's all the theory, but why does any of this actually matter? Let's take a look at how these tools are being put to work to solve some really interesting real-world problems. So K-means, the sorter, is an absolute workhorse in marketing. Imagine a company wants to create, say, 5 distinct customer profiles. They can use K-means to sort their entire customer base into those 5 groups based on things like purchasing habits. This lets them stop using a one-size-fits-all approach and instead create super targeted campaigns that actually resonate with people. And what about the genealogist? Well, in biology, it's fundamental. Scientists use it to create those evolutionary trees you see, showing how different species are related based on their DNA. Or think about HR. A company could use it to find natural groups of employees based on their skills, helping them build better teams or figure out where more training is needed, all without any preconceived ideas about how people should be grouped.
And this right here, this is where the detective truly shines. A bank analyzes millions of transactions every day. The vast majority form these dense clusters of normal behavior, buying groceries, paying bills. But a few transactions, the ones that are far away from any of those dense regions, they get immediately flagged as outliers. Those are the potential cases of fraud that need to be investigated right away. It's literally finding a needle in a haystack, and that's what DBSCAN was born to do.
So when you take a step back and look at all 3 of these tools, you start to see that they all share one incredibly powerful purpose. So what's the big takeaway from all this? Simple. Clustering gives us a map. It lets us see the hidden structures in our data, whether that's grouping customers, finding patterns in scientific research, or detecting fraud. It's the process that turns that raw chaos of data into actionable, strategic knowledge. And that really leaves us with one final thought. From the way galaxies form in space to the way ideas spread on social media, natural groups and patterns are absolutely everywhere. The real question is, what other hidden structures are out there all around us, just waiting for the right tool to come along and discover them?